Okay, so we are on to number 6. So 6 is asking us for the limit as x approaches 0, 1 over x plus 4 minus 1 over 4 over x. So it says the limit as x approaches 0, so we're going to try to plug in, do direct substitution. Well, if you notice, we're going to have 0 in the denominator, so we can't do that. So if you take a look, the next step is to try to factor. Well, you can't factor when we have fractions like this. So we're not really going to be rationalizing either. What we're going to be doing here is we're going to add these fractions together to see what happens. Technically subtract, but I'm going to add fractions if I have fractions. So I'm going to make it 1 over x plus 4 plus negative 1/4, because you know I like to add instead of subtract. So we're going to make these have common denominators. So this one needs a 4, this one needs an x plus 4. So we will have 4 times 1, so 4, minus x and minus 4. And then we're just going to leave it as 4 times x plus 4 in the denominator. So in the numerator, we just have the 4's will cancel, so just negative x over 4 times x plus 4. Okay, so that we just added the fractions on the top. So we technically still have this negative x over 4 times x plus 4, and it's still all divided by that x that was already there. So I'm going to do same change flip because we have a fraction divided by a fraction. So think about this as being x over 1, so we'll make it 1 over x. That'll allow those x's to cancel. Remember, the goal is to get something to cancel. So what we have left with is we have negative 1 over 4 times x plus 4. So now that we've had those x's to cancel, we are going to bring down our limit as x approaches 0. So we're going to have negative 1 over 4, because now we're going to do direct substitution of 0 plus 4. So we're going to end up with negative 1 over 16 for our final answer for our limits. Okay. So, when you have limit as x approaches a number, okay, you want to make sure that you try to do direct substitution first. Always try it, because that might be all you have to do. Then you're going to try to factor. If it's something that you can't factor, you might have to rationalize like we did on number 5, or you might have to add fractions together. Those should be the only techniques that you really have to work with, especially in the pre-calc. Okay, so moving on. Now we're going to be looking at the limits as x approaches infinity. So instead of it saying x approaches a number, it's going to say x approaches infinity. So it says when x approaches infinity or negative infinity, it doesn't matter which one, you're going to be looking at the end behavior. So you're going to be seeing what happens at the end of the graphs. So the line y equals L, if that is a horizontal asymptote, then when you're finding the limit as x approaches negative infinity or positive infinity, the answer should be that horizontal asymptote. Okay, so when you're looking at end behavior, remember we're talking about horizontal asymptotes. So these are rules that hopefully you remember. So I have them written out formally here. I'm going to write them in a kind of different way. But for number 1 and number 2, they kind of mean the same thing. So looking at 1 and 2 on the sheet, this is talking about having a small degree over big degree. Now, if you remember when we talked about horizontal asymptotes and end behavior, so small degree says the numerator is less than the degree of the denominator, or here if it's just a constant, so like 3 over x to the third. So small degree over large degree, then remember that limit will be equal to 0. So then you have the horizontal asymptote at 0. Okay? The third one says if the numerator is greater than the denominator. So the third one is talking about when you have big degree over small degree. Well, that's when you have the horizontal asymptote doesn't exist. But for horizontal asymptote here, for our limit, we're going to be saying the limit approaches infinity. Okay? And then for the fourth one is when you have the same degree over the same degree. 1 here. And then if you have the same degree of the same degree, remember you have to use the constants. So the coefficients over the coefficient. Okay, if you remember my little trick for the first two parts, if you have a big person sit on top of a small person, there's no person left. Okay, so there's no horizontal asymptote, but that's going to be infinity when it approaches here. Small person over big person, then we're going to have 0. And if they have the same degree, you're going to use the coefficients with the degree highest exponent for the top and the bottom. So, first example, we have the limit as x approaches infinity of 2x squared minus 3x plus 1 over x minus 5. Okay, so here's where you just have to be careful because these are all going to be thrown in together. We're doing the limit as x approaches infinity, so you can't do any plugging in there, okay? So you have to look at end behavior or look at horizontal asymptotes. So we're going to be looking at horizontal asymptotes. When we're looking at the degree, we're looking at the highest exponent. So the highest exponent there is 2. The highest exponent here is 1. So this is where we have big over small. Well, big person sits on top of small person, no person left. So this limit is going to be approaches infinity. Okay, it means there's not a horizontal asymptote. Alright, so if we look at the second one, we have the limit as x approaches infinity, x squared plus 1, 3x squared minus x plus 7. Okay, so we have the limit as x approaches infinity, so no direct substitution. We're looking at horizontal asymptotes. This is a degree of 2, and this is a degree of 2. So these is same over same. So if it has the same degree on top and bottom, remember I have to look at the coefficients. So the coefficient from the top one is 1, the coefficient from the bottom is 3, so this limit will be giving us 1/3. Okay, so looking at the third one, the limit as x approaches negative infinity of x over x cubed minus 8. So because it's the limit as x approaches, and it doesn't matter if it's positive or negative infinity, but we're going to be looking at horizontal asymptotes. The degree on top is 1, the degree on the bottom is 3. So this is a case where we have small over big. When we have a small degree over big degree, this is when it approaches 0. Okay, and then the last one here, a little different. The limit as x approaches infinity of cosine x. So guys, cosine, I mean, we do not have a rational, so we don't have a numerator and denominator here, so there's nothing to look at. But we are doing the limit as x approaches infinity, so we're still looking at end behavior. So if you think about a cosine graph and a sine graph, they look the same, okay? They just start at different pots. But the highest it can get to here is 1, and the lowest it can get to here is -1, okay? But when you're thinking about end behavior, so what's happening on the end, if we're thinking about right end behavior because that's positive, right or left is not going to make a difference. But if you go on the right side here, it goes up to 1, down to -1, up to 1, -1. It's never approaching one single number. So this doesn't exist. And it's because it doesn't approach a certain number. This is oscillates between -1 and 1. So it just keeps going -1, 1, -1, 1. It doesn't give you one certain number. So that's going to be does not exist for that. Okay, so next thing we have is we're going to be looking, these are called relative rates of change. So sine and cosine graphs are going to move a whole lot slower than when we have exponential. So think about sine and cosine have a waves. Exponential, it's going like 5 times 4 times 3 times 2. So it goes a lot faster. So whenever we're looking at, these are going to be set up as rational functions. The ones that are faster will overtake the slower ones, okay? So what's going to happen here, it says if the numerator overtakes the denominator, then the limit doesn't exist. Okay, so I like to just think about numerator over denominator. When the numerator overtakes, so that means goes faster, that means the limit doesn't exist. Alright, but then if we have numerator, denominator, if the denominator overtakes, then our limit is going to be 0. Okay, so numerator overtakes doesn't exist, denominator is going to give us 0. So let's look at some examples of this. So if you look at the first one, we have the limit as x approaches infinity of e to the 2x over x minus 1. So when are you even going to use this? Well, it's going to be the limit as x approaches infinity or negative infinity, so you can't just plug in. And in behavior, they're not both just algebraic, so it's not like x squared on top. We have two different types of functions. So because we have two different types of functions, if you look at your list, go back to my list, we just need to figure out which one's going to go faster. So e to the x would fall here. X minus 1 would be more of algebraic. So our e to the 2x is going to be faster. Well, it says if the numerator is faster, then the limit doesn't exist. Okay? So then if we take a look at the second one, we have the limit as x approaches infinity of sine x over x squared. Okay, we're looking at the limit as x approaches infinity. These are not both just algebraic x squared or like polynomials is what I'm trying to say. They're different types of functions, so we have to see which one's going to go faster. So sine is the slowest, whereas just x squared goes faster. So if the denominator overtakes, that means that the limit's going to be equal to 0. And then the last one we have, the limit as x approaches infinity. And guys, these can work for negative infinity or positive infinity, doesn't matter. X to the 7th over ln of x. So we have the limit as x approaches infinity, so we can't just plug in. So because these are two types of different functions, we're going to have to see which one overtakes. So ln is very slow, like sine and cosine, so x to the 7th is going to overtake. Well, if the numerator overtakes, that means it's going to be does not exist. Alright.